Okay, let's keep working on our checkerboard test workflow, right? So for now, um, for now let's uh, so we have created all the WF strain fields, right? And then we have created all the synthetic silent worms for each of the source, right? Um, the next step is supposed to actually create uh, the so-called wave field perturbation kernel, or WPK. Right. In the past, I was calling it Southern perturbation kernel, or SPK. Right. But the Southern perturbation kernel looks like it's just using like a one source and one receiver. Right. But sometimes you may want to use like a multiple source or multiple receiver when you actually derive the measurements. In that case, it's not exactly Southern perturbation kernel. It's gonna be a wave field perturbation kernel. So so that's why I changed the name to wave field perturbation kernel, or WPK. Um, and in order to actually run that piece of code, we have to actually pick some waveform windows. It's not exactly the waveform itself, but the windows, the time windows used for isolating or selecting the waveform that's going to be used for making the measurements. This particular time window, right? That's going to be um, that has to be picked either by hand or by using some kind of automatic or semi-automatic algorithms, right? So in Wei's inversion, his DG synthetics were picked by hand. Uh, Maybe not exactly by hand, but he has a semi-automatic procedure for picking the Rayleigh wave on the vertical component. It's pretty much fundamental mode Rayleigh wave that has a more or less constant move out with respect to source receiver distance. So, so because of this very relatively simple um, waveform used in his inversion, so he was able to devise a semi-automatic way for extracting time windows or constructing time windows for isolating those fundamental mode radio waves um, using some technique called slant stack. Right, slant stack basically you stack the seismograms according to a slope. This slope is based upon the move out. The you basically just try different slopes and see which slope actually gives you the maximum energy, and that slope is going to be the optimal speed or group velocity of that fundamental mode radio wave. And then that speed is going to give you a prediction about the arrival time based upon the source receiver distance. And then this arrival time can be used for constructing a time window, right, around centered around that predicted arrival time, right. Um, so now uh, let's look at how do we actually continue. One of the things that's kind of useful to do when you are waiting for the simulations to complete, one of the things that's kind of useful to do is to actually check if the model output, and then once the kernels have finished computing, it's also useful to actually do a check on the kernel outputs, right? And both checks are going to require a binary that's called AGP. Assemble grid partitions. AGP represents assemble grid partitions, and this shell script is going to call AGP, right? And then it's going to require like this many inputs. So the model input, the control file for the inversion, right? And then the model, the prefix for the model, basically, right? The prefix for the model, because it's not actually having all the partition IDs behind the model name, right? And then the number of parameters per recording grid point, right? Um, so for velocity model, it's VP, VS, and density, right? That's 3 doubles per recording grid point. And then that's the output. It's gonna create a one binary output. It's not sort of like 72 binary outputs. It's just gonna assemble all the 72 binary outputs into like a one binary output in the correct order, of course, in the correct order, right? Um, and then 0, 2, 0, 2, 1, 0. 0, this 0 means if you want to actually multiply the assembled property with the cell volume. Right. This option is used just for kernels, but for every other model parameters, you don't want to multiply with a volume. Then you don't have to. You must fix this value to 0. If you want to multiply with volume, cell volume, then you have to change this value to 1, right? And then 210 is a way for how do I say, permutation. So the recording grid point is gonna have x as the fastest direction and z as the slowest direction, right? But when I write out this particular output, dump output, I want to change the ordering of the fast and slow directions. I want to store z as the slowest dimension, right? Uh, no, what I said was wrong. So by default, if you do not specify the permutation, then it's gonna reorganize all the binary data so that it's following x, y, and z. So x is gonna be the slowest, y is gonna be the next, and z is gonna be the fastest actually, right? It's gonna destroy the ordering of the recording grid point. But if you want to sort of preserve the ordering of the grid points of the recording grid points, then 210, right? So 2 means z direction has to be the fastest, the slowest. Z direction has to be the slowest, and then 0 means x has to be the fastest, right? So that way it's gonna preserve the slow and fast directions in the binary output, right? And then this binary output can be read by using MATLAB. You can read it from MATLAB, and then if you want to make cross sections or plot map views, you can do that. It's not really that complicated. And that's for doing the doing the model, right? And then once you have the kernels, for now we don't have the kernels, right? And that's how you can actually call it. The format is pretty much the same, right? The control file, and then the prefix for the kernel outputs. And then for every grid point, we have like 21 kernels. Why we have 21 kernels? Because it's frequency dependent group delay, right? And then we have like 21 frequencies for every fundamental mode Rayleigh wave. So for every time window that we picked on a specific sidegram, we're gonna compute like 21 kernels, right? And these kernels are for frequency dependent group delay measurements made on that particular waveform, selected waveform, right? And then this is just with respect to shear velocity, right? So if we want to compute for p velocity, then that's going to be double. That's going to be 42, right? So every grid point, every recording grid point is going to have like 42 kernels, that kind of thing. And then that's again a binary dump. And this time we're multiplying with volume, right? And then 210, that's the permutation to which is the fast direction, which is the slowest direction, which may have consequences when we actually try to actually solve the linear system using LSQR, using the parallelized LSQR, because the fast and slow directions controls the bandwidth of the damping matrix. I mean, by the bandwidth, I mean the diagonal, right? So the efficiency of the parallel LSQR code depends upon how wide the damping matrix, the non-zeros in the damping matrix are surrounding the diagonal. So we would like to actually minimize this kind of a bandwidth, right? And doing this kind of permutation is one of the ways for achieving that. And again, this binary file can be read into MATLAB and then make cross sections or make map view plots, that kind of thing. So AGP, assemble grid partitions. That's one of the useful commands. So now let's get back to talking about the kernel, the windows, right? So in order to actually get the windows, we have to actually retrieve the synthetic subgrams. The synthetic subgrams are stored inside of each of the simulation directory, right? And in this particular USGS ASCII format. And now let's Now let's try to collect all those synthetic sideworms using this particular synthetic collector script called syn collect. Right? It's just a very simple Python script that's going to loop through uh, each of the simulation directory and then try to extract the vertical component synthetic sideworm, just as a Z component, and then put them into like one text file. Do I have a syn collect shell script that's going to call that Python script? It looks like I don't have it. But that's okay because this syn collector is actually quite simple. Let me look at my history. Looks like I don't have a history. So the first input is supposed to be the source receiver list file, I think. And then where the folder FWF directories are and the component ID. If it's a Z component, then it's supposed to be 2, I think. No, it's supposed to be 3 because the first column, the zeros column, is supposed to be time, right? So it's time and then X, Y, and Z, right? So time is 0, X is 1, Y is 2, and Z is 3. So and then output file name. So it's going to try to actually collect all the vertical components synthetic sideworms. Let me see. Let me try to understand how the code actually works. Okay, I see why. The first list is actually a source receiver list. So this is actually a list of the source and the receiver for each of the synthetic sideworm. Right. So what does it look like? Right. It's supposed to look like source receiver list.dat, this file. Right. So it looks like that. So 5 is going to be the source ID. 31 is going to be the receiver ID, right? That's for one sideworm, and then you have to sort of do this for every sideworm. So for the fifth source, we have like a bunch of receivers, right? And then yeah, that's like a lot of them, right? And then how many sideworms do we have? 6,371 sideworms. So in this particular inversion, he was using 6,371 synthetic sideworms or ambient screens functions. Right? It's a relatively small box, and then he's got this many ambient screens functions inside of it. Right? It's actually quite a lot. It's a lot of ambient screens functions. It's a lot of data basically for this relatively small box. And then the output file is gonna this is the output file, I think. It's supposed to have like this many rows with one more row because the first row is gonna be time, right? So the first row is gonna be the time axis, and then all the rest of the rows are gonna be the vertical component of synthetic sideworms that's corresponding to each of the line inside of this source receiver list.dat file, right? Yeah, once this file is created, what I did was to actually copy. No, not this file. Once this synthetic list file is created, what I did was to actually copy this file over to my local machine where I can run MATLAB, right? And I have a MATLAB, very simple MATLAB function for picking the envelope. It's not as accurate as the slant stack-based semi-automatic procedure we has been using, right? But it's accurate enough. It's accurate enough. So what this function is going to do is it's going to take the synthetic sideworm, right, and then the time axis for that particular synthetic sideworm, and then some ratios, small r, big R, some ratios, and then a minimum window width, right? So what this code is going to do is it's going to do a Hilbert transform on the synthetic sideworm and then take the absolute value of it. And then that's going to be the envelope of the synthetic sidearm, SE, right? And then it's gonna identify the maximum on this envelope. So this part is probably similar to the slant stack procedure based upon with slant stack procedure, right? And then it's gonna identify the location of the peak, and then it goes from that peak backwards in time, try to find a first point where the envelope amplitude reduces to like a small r. That's like the if this small r is like 1/5, then it's the backward track is gonna stop when the amplitude of the envelope reaches like a 1/5 of the peak amplitude, and then it's gonna do a forward sort of search, right, to find the first time point where the amplitude of the envelope reduces to like reduced to 1/5 of the peak amplitude, and then it's gonna record the two time T0 as T0 and T3. And then if T0 and T3 if the width is smaller than the minimum required width, it's going to extend it. It's going to extend it to the minimum time window width. And then the time window actually requires like 4 points because it's a cosine window, so it's got a flat part in the middle. And then this flat part is like a portion of the entire window. And this portion is capital R, right? And the parameters I used was what? I can't remember. So W equals to, okay, 0.1, 0.1, 1/10, right? And then the minimum timing window is like 0.2 seconds, right? So that was the parameter that I used for getting the envelope, for getting the time window, right? And then this time window was then saved as an ASCII file called source receiver envelope win. It's saved in this particular ASCII file, and this ASCII file was then transferred to Cheyenne, right? That's source receiver win, right? Well, envelope win, source receiver envelope win. Right, that's the time windows. So once I've got the time windows, I can run a script to actually create all the .win files from this master window file. This .win file has to follow a specific format. So it's gonna read the source receiver list, right? It's gonna read the envelope win file, and then it's gonna read the frequency list. At those frequencies, I want to compute my frequency, my group delay kernels, right? And then the frequency list is just a very simple file that lists all the frequencies I want to compute the kernels on, from 10 to like 30, with like 1 hertz of spacing, right? In Wei's inversion, he was using 0.5 hertz of spacing from 10 to like 30 hertz. So his measurements was kind of denser. And then it's gonna try to actually create the correct window file based upon the source receiver ID for that particular synthetic isomer, right? And then the window is gonna be named as this .txt.win, right? So and then for every window, it's gonna write one line. So if you have like multiple windows picked on the same sideworm, all those multiple windows has to go into the same file, and then the same file has to be named as .txt.win with the source receiver ID kind of appended in front, prefixed in the front. And then each of the window line has to follow this particular format. 2 means the component number, and then 1 is the measurement type. If there's going to be frequency dependent group delay, it's going to be 1, right? And then if it's different, for example, broadband cross correlation delay time, that's going to be 0, right? And then the window, the 4 numbers for the window, and then the frequency. If the type is 1, that's a frequency dependent thing, then it's going to require a frequency list at which frequencies you want to compute the kernels, right? So if we want to look at the one example, let's still go back to FWF P003, right? Let's just look at this particular window file, right? Cat. So it's got just one line, right? Because we have only one window on that particular hardware, on this particular synthetic hardware, right? If you have multiple windows, then there's going to be multiple lines, right? And then each of the lines starts with the component ID, 2 for vertical component, 0 for X component, right? And then 1 for measurement type, and then followed by the 4 numbers for the time window. That's 1, 2, 3, 4, 4 numbers, right? And then followed by the frequencies at which we want to compute the kernels, right? So that's sort of the window file, right? You can generate this kind of window file using whatever script you want to use, right? That's tied together with the measurement process. Once the measurement process is kind of fixed, the procedure for creating those window files becomes relatively straightforward. But here we are not really, our focus is not really in that. So once we've created all the window files by using winging.py, the next thing we have to do is to wpk.sh, right? So it's going to call WPK, the wave field perturbation kernel binary, and then the first input is still the control file, and then it's going to require a list of all the window files. So win list 2, if I just do a head of win list 2, it's just a list of all those window files. So this list can be generated by just using ls. All you have to do is to specify the directories, right? And then star.win. That's going to give you a list of the windows, and then all we have to do is to actually pipe it into like this particular file, right? That's how this window list was created. And then because the source time function is not really a direct delta function, it's actually got a source time function, right? The source time function is specified inside of the control file, right? Right, that's the source time function. But this source time function can have a different time sampling interval and also a different format than that's required by WPK, right? The file that's the source time function that we are going to use in WPK is actually generated by the SW4 code during the forward simulations called g1.dat, right? So for every simulation, so suppose. So for inside of each of the simulation, after SW4 finishes executing with write info equals to 3, it's going to create this g1.dat file. And this g1.dat file is basically just the source time function resampled onto the time sampling interval that's used for computing the synthetic sonograms. So the time sampling interval here is going to be identical to the time sampling interval used in computing the synthetic sonograms. So that's gonna be the last input for the WPK code. Right, that's the last input, the source time function for WPK code. So in principle, you could actually specify this source time function for every window inside of this win list. So this win list can have like multiple columns, right? For this particular synthetic window, we have a different source time function. For this one, we have another source time function, right? In principle, it could read like 2 different columns. But if you have just one column, then it's going to take this particular input, the last command line argument, as the source time function that's going to be used for every synthetic hardware, right? And then this WPK code is going to go through every file inside of this window list, and then create the corresponding WPK file, right? And again, this WPK file is an ASCII text file that's going to be read by the kernel code. right? This time it's gonna be quite long, right? Because you have like 21 frequencies, and each frequency actually is one column, right? So it's gonna have like 21 columns. And then the first two numbers are headers. The first two numbers of each column is header. That's telling the code the starting and ending index of the non-zero part of the WPK, right? Um, um, so when we do the scattering integral, which is actually a convolution in time, then and then an integral in time, then it's gonna be it doesn't have to actually integrate through all the time samples. You can just stop at the whatever time sample at which the WPK becomes all zeros, right? Um, and then that's pretty much the WPK code, right? That's the WPK code. So once all the WPKs are created, we are pretty much ready for computing the kernels, right? How do we actually compute the data sensitivity kernels, right? Um, the first thing to do is to still create all the directories first, the kernel directories. So if you look into the kernel directory, it's organized like that. So that's like the source, right? That's the sources, and then under each of the source you're gonna have receivers, right? For this particular source you have lots of receivers, right? And then underneath each of the receiver, that's actually the kernel outputs. That's the kernel outputs, right? Um, so in order to actually create the kernel directory, I have a Python script called kdrgin, right? So it's gonna just it's gonna generate the list of all the WPK files, and then according to those WPK files, it's gonna try to actually create all the kernel directories following that particular following that WPK's file name, basically. And then it's gonna create a soft link to link the WPK file into that kernel directory, right? Um, so that's how the kernel directories are gonna be organized, right? It's not really that difficult to create the directories, but later on I might want to sort of integrate this particular script into my um, inversion code, right? Because I like this particular structure, and I want to fix it to this particular structure so that I can use it later on instead of writing Python scripts every time, right? And then another thing that I have to create is a WPK list. That's gonna look like this kind of thing. Again, all those WPK lists can be actually created by after the kernel directories are generated and all the soft links to the WPK files has been placed inside of each of the kernel directories. I can just do a list, do an ls, right, and then just list all the star.wpk, and then just put it into WPK lst2, right? The important thing is that I have to actually list all the files. I have to list all the WPK files inside of the kernel directories, the soft links inside of the directories, not the original ASCII text files inside of the synthetic, inside of the forward simulation directories, right? Again, this is something that I need to actually fix inside of my inversion codes, not as a kind of a procedure that the user has to remember about. It has to be fixed. It has to be fixed. User cannot actually cannot actually touch this part of the workflow because nobody is going to remember that. Um, um, and then after the kernel directories are created, the WPK list is created. we can run this particular script called kjobjing, right? And this kjobjing is gonna use a template that's called a run dsk.sh, and this run dsk.sh is actually a template for calling the dsk binary. Right. And the dsk code is actually a parallel code, so we have to run it in parallel by using MPI. The first input is still the inversion control file. We have to specify the absolute path because on the computing nodes, it has to actually be able to actually find this particular file on the computing nodes. And then the forward directory, the directory for storing all the forward simulation results, and then the WPK list, and then the kernel directory. And then this one means I just want volume kernels. I don't want surface kernels. Right, so I have a bunch of codes for computing surface kernels. Surface kernels means it's the sensitivity with respect to the depths of a particular interface, right? That's the surface kernels. That can be used for purposes that's kind of similar to migration. And then this Python script called kjob_jing is going to use this particular template and then replace all the test and then all the input files. So it's going to do a split of this particular WPK list 2, right? And then the split of the input file is just going to be used for the second part of the job script running post processing, but for the first part it doesn't, right? So or does it? Okay, so it also does that. Okay, so for the first part it also splits the WPK list into like multiple ones, and in each of the file it's gonna have like 100 WPKs, and then it's gonna create a bunch of output scripts. So and then maybe we should just run this script once, kjobjing.py, and then we're gonna have all those job scripts. So the reason that I want to sort of split the WPK file into like multiple ones, like these kind of things, is because for now the kernel code can only use like 72 cores per job, right? But the Xiaoyan is like a big machine. Like it can run a lot more kernel codes simultaneously. So if you split the WPK file list into like multiple files, then you can submit all those kernel jobs to run simultaneously, right? So each of the kernel job is going to look like that, right? So by the way, DSK means data sensitivity kernel. That's a shorthand for data sensitivity kernels. So it's going to replace the test with the job name with the DSK00, that kind of thing, and then the WPK list is going to be this particular file, and each of those the output from the split command is going to have like 100 WPKs in them. That's like a much shorter list, right? And then the kernel output, I just want the volume kernels. So each of the file is going to look like this kind of thing, and then for the second part, it's also going to create all the post-processing jobs. So KPP. So KPP is also coming from this template script. It's gonna call this binary called kernel post-processing. So KPP. Again, it's a parallel binary, so we have to run it using MPI. The inversion, the control file, the WPK list, a threshold. So this post-processing is gonna threshold all the kernel values. The kernel values that's smaller than this particular ratio times the maximum kernel value for that particular WPK. So it's gonna so the threshold is a relative threshold. It's not an absolute threshold. So it's gonna be relative to the maximum value of a particular WPK and a particular kernel type, right? And then this is some kind of scaling. So the kernels can be scaled. It's called preconditioning, right? You can scale the kernel somehow. For this ambient noise inversion, it's a surface wave kernel. Surface wave kernel has sensitivity decreases very fast with depth, right? And this scaling value can allows us to um, boost up the kernel values at larger depths, so they are not as small as the raw kernel. The side effect is that the inversion results after you actually finish computing the LSQR, running the LSQR code, has to be scaled back. So the model parameters that you are actually inverting for has to be scaled back after you have finished solving the linear system. And then 210 is again the permutation, which direction you want to sort of store fast and slow direction. So Z is going to be the slowest direction, and then X is going to be the fastest direction. Right. And then we have a bunch of KPP scripts that can be submitted, right? And then all we have to do is to actually put to some if you want to submit all those jobs in like a one command, we can just do a ls, right? Do an ls, say run kpp.sh, and then pipe it into awk, and then print q sub, right? And then followed by the first column, right? And then that's gonna, oh sorry, I forgot to put a space. Right, that's that, and then you can actually pipe it into a particular job script, a particular shell script, right? And that shell script is here, q sub ko, right? Q sub ko. That's so by running this particular shell script, it's gonna submit all those post-processing jobs. For DSK jobs, you can also do the same kind of thing, right? And then that's gonna create all the kernels. Right. Once all the kernels are computed, I can actually do a check, for example, right, for using AGP to look at the kernel, to look at the spatial distribution of the kernel, see if it actually makes physical sense, right? So that's how the kernels can be actually computed, right? So after the DSK code is run, after the post-processing is run, the next step is to run. So in the post-processing, I didn't actually talk about the scaling file, right? The kernel scaling file. I didn't actually talk about how the scaling file was created. It's called ksg.sh. Right. So it's gonna call this sequential binary. It's a serial binary, and then inversion control file, right? For now, it's doing this kind of a doing this kind of a polynomial, basically. So this polynomial is going to have a coefficient of 1, right? And then on the on the x component, the power is 0. On the y component, the power is 0. On z component, the power is 0.5. It's a polynomial. So so the scaling is gonna depend upon scaling is gonna equal to 1 times x to the 0th power multiply with y to the 0th power multiply with z to the 0.5th power, right? So it pretty much just depends upon z, right? So x to the 0th power equals to 1, y to the 0th power equals to 1, right? So 1 multiplied with 1 multiplied with 1 doesn't have any kind of effect. So it's just pretty much just the z to the power of 1/2, right? So and then the output file is going to be written into this particular binary, and then we have this kind of permutation 210, right? So this particular output file ksg.out is going to be used in the KPP in the post-processing, right? That's this command line input. So this command line input can be this particular scaling file, or it can be just a constant. If you put like 1.0 here, then there's no scaling at all. The kernel is going to be used as is. It's not going to do any kind of scaling. But this KPP code is going to do a few things. It's going to multiply with volume, right? It's going to so all the kernel values are going to be multiplied with the cell volume for that particular kernel value. And then it's going to do this kind of thresholding, right? It's going to treat values, kernel values, as too small as zeros. And then it's going to save the output as in a row column format for just storing the non-zeros. It's not going to store all the zeros, so it's going to reduce the storage by quite a significant margin, right? So if we look into one of the kernel directories, say P003, P011, right? It's got two different kinds of output files. This KV stuff, that's for volume kernel output, right? It's got a partition ID following it. That's because each partition computes its own kernel, right? Each process computes the kernel for that particular partition, right? So these are the outputs from the DSK run, from the DSK code. And then the KPP is going to assemble all those different partitions together into like one file, and that one file is going to be compressed by removing all the values, by treating all the values below the threshold as zeros, right? It's not going to store all the zero values, and that's going to be a binary file inside of the KNZ, kernel non-zeros, and then it's got an info file that's telling us the dimensions and the number of zeros, right? So it's got 21 kernels, and the kernels are stored on a grid that's like a 66 by 55 by 55. 55, 55, that's the two horizontal dimensions after a decimation by 5. 66, that's the z dimension. So it's gonna start from the slow dimension and then to the fast dimension, right? And then 21 kernels are separating like 21 WPKs and one kernel type, right? If you have like multiple kernel types, this is probably not 1, and this is not 21 anymore. It's the number of WPKs, and then the multiplication of these two numbers is supposed to equal to this number, right? And then for this particular kernel, you have this many non-zeros, right? It's a very small percentage of 21 times 66 times 55 times 55, right? So after compression, the storage is like much smaller, right? After post-processing, I mean, after post-processing. And that's how KPP is run, right? That's how the kernels are created and post-processed, right? And then the next step is to run another code called KTR. KTR means kernel transpose. So for now, all the kernels are stored in a row-wise format. Basically, every WPK is stored in like one row. The kernel for each WPK is stored in like one row. But in order for the WPK to run very efficiently, for the LSQR code to run efficiently, we have to actually transpose the kernel into a column-wise format, right? We have to actually at least record the column information, right? The non-zero information for different columns of the kernel matrix. And that's done by using this KTR. Again, it's a parallel code. You have to run it using MPI. And then it's going to take just one command line input. That's KNZ list. So what this KNZ list is going to look like, it's going to look like this kind of thing. Let me do a head. It's going to look like this kind of thing. So the first row is like quite important. So that's how many columns we want in the kernel matrix. Right. The number of columns is basically the number of model parameters. So here we are inverting for VS, right? We are inverting for VS at every recording grid point. So every recording grid point is like 66 by 55 by 55, right? So if you multiply these three numbers together, 66 in the z direction, right? Multiply with 55 in the x and y. right? That's exactly this many numbers. So the column number of the final assembled kernel matrix is supposed to have this many columns. And then the next two numbers are some buffering number, which cannot be too big, because on distributed memory machines, the memory for each core is actually quite limited, right? So these two numbers actually control how much memory each core can actually use. You don't want to set these two numbers to be too big, right? You want them to be um, compatible with the amount of memory per core on your cluster. And then that's going to be the directory for storing the transposed kernel outputs. Right. So for now, this directory may not exist for you, but you can just make this directory. It's supposed to be inside of the kernel directory, right? Called KTR. And then the following it is just a list of all the KNZ files. Again, you can just generate it according to this particular by using -ls, right? But here there's a number following it, and then 21 following it. So 21 just the number of WPKs, or the number of the number of measurements, inside of each of the KNZ file, right? Each KNZ file is not just for like one WPK, it's for like 21 WPKs, right? Because we have like 21 frequencies. And then this number is actually the size of the file. So for kernels that has lots of non-zeros, the file is going to be quite big, right? And then the files are sorted according to the size, or the lists, or the KNZ files. So I have to do this kind of a sort equals to size thing, and then star KNZ, and then put it into a KNZ list, right? That kind of thing. Maybe do a pipe, right? We have to do a pipe AWK, and then print. Yeah, I don't exactly remember the column numbers, but this particular thing is used. This particular line of code is used for generating all the rest of the kernel of this particular file, right? This KTR is actually quite efficient. It's going to take a very short amount of time to complete the counting of non-zeros and do the transpose, right? And then all the outputs are going to be stored inside of the kernel directory called KTR, right? And for now, the output files are not exactly there yet. It's because I have concatenated all the different output files into like one file by using just a cat. So the output files are going to look like ktr.ou, and then followed by 8 digits, right? And then all I have to do is to concatenate it into like one file, ktr.ou, right? And then here, if you look at my ktr.ou star, I've got lots of these kind of concatenated files that I have experimented with, right? Some of them are XYZ, which is a different kind of a permutation, right? Which direction is faster? X is slow, Z is fast, right? ZYX, Z is slow, X is fast. And then with different kind of scalings, right? Z equals to 0.5, Z equals to 1. The Z to the 0.5th power, Z to the first power, that kind of thing. So every time you change the post-processing procedure, you have to redo the KTR, and then redo the concatenation to actually come up with a new file, right? And that's pretty much all the kind of processing that's needed in order to get the kernel part, or kernel matrix part of the LSQR that's going to go into the LSQR code, right? And this video is probably too long. Let me stop here.